All right, so the way that we're going to go through our section on simple machines is we'll just talk about some basic information related to simple machines. We need to talk about how we calculate the mechanical advantage of a machine, and then we'll go through each of the types of simple machines and talk about specifically how they're used, real-life examples, how we measure their mechanical advantage. Cartoons there. So before we can get really to simple machines, we have to talk about a couple things. First is this term work. And so in physics, work has a specific definition. And basically, work is done when a force is applied to an object and the object moves. So that's what we mean by work. So if I lift this board, I'm doing some work. I'm applying a certain amount of force to this board, and it's moving a certain distance. Okay, so work is being done. So can you guess? So what do we need to know to calculate how much work is being done? I need two variables. Nicole? What's up? You know, how am I going to calculate? What numbers am I going to use? So let me ask you this. I just lifted that board. Now I'm lifting my keys. When am I doing more work? Courtney? Yeah, so mass is important, or we'll say weight. And what's the other factor I need to take into account, Jonathan?
How much force do you apply?
Yeah, so the other factor is the force, and then the distance. So if I'm talking about lifting my keys, I lift them this much, I've done a certain amount of work. If I lift them this much, I've done a different amount of work. I've done more work now than when I do this. Okay, so work requires two variables: the force applied and the distance. Yeah. So we abbreviate that. W equals F times D. Work equals force times distance. So we're going to think about an example. If I'm pushing a box and I have to apply 10 newtons of force to move the box, and the box moves 8 meters. It's a simple problem to solve. But again, I need to follow my steps by writing out the formula. Second step, substitute my numbers. Third step, solve with a unit. Now, obviously, we know the number is going to be 80. So what would the proper units be here? Joey? What's that? Well, what would our units be for this? If we're solving this problem, it would be 80 what? Grant?
Newtons per meter.
What's that?
Newtons per meter.
Not newtons per meter. Per means slash. Per means divide. Like miles per hour. So it's not per, Emma.
Newtons times meter?
Newtons times meters. But we have an abbreviated unit for this. We have an abbreviated unit for Newton times a meter. And it's named after a 19th century physicist. It's called the joule. Joule. And we abbreviate it with a capital J. So we've done 80 joules of work here. So a joule is the force of 1 Newton applied moving an object 1 meter. That's the definition of a joule. machines, what they do is they allow us to do our work in a different way. And they can do many different things. But the key thing to know is they do not change the amount of work that's being done. So if I have this weight in my hand, and I need to move it to the top of this box, I've done some work. I've applied a force for a certain distance, and I've done work. I could use a simple machine to also get the weight from the table onto the box. But the amount of work I'm going to do is going to be the same. Even whether I'm using a simple machine or not, the amount of work that I'm doing is the same. What simple machines allow is they allow us to do several things. They can transform energy from one form to another. They can transfer energy from one place to another. They can multiply our force. They can alter the speed of an object or change the direction of a force. But even though they do all of those things, they don't reduce the amount of work that needs to be done. And that should be clear after we finish up talking about a couple of these simple machines. Now, when we use a simple machine, when we have a simple machine, one thing that we often want to know is, well, how much does it help us? And we call that its mechanical advantage. Okay. And there's two types that you're going to have to understand and calculate. They're called ideal mechanical advantage and actual mechanical advantage. Okay, so mechanical advantage is a measure of how much help the machine gives you. So actual mechanical advantage is mechanical advantage that takes friction into account. When we use a simple machine in real life, there's some friction. Because we have moving parts. So there must be some friction. And so when we're calculating the actual mechanical advantage a machine is giving us, that takes friction into account. When we calculate actual mechanical advantage, we use the forces that are being applied to do that. We use these forces. Ideal mechanical advantage is the other type. And ideal mechanical advantage, it does not take friction into account at all. It's sort of a theoretical mechanical advantage. That theoretically, this machine should give me a certain advantage. And it does not use forces. It uses distances in its calculation. So if we imagine a simple machine, we could understand how we calculate these two things. Now, we haven't really talked about any simple machines yet, but we can use this as an example because it's fairly obvious. What type of simple machine would this be?
Seesaw.
Yeah, a seesaw is a type of
Lever.
So we call this a lever. We'll learn much more about them towards the end of this section. But this woman's trying to lift this boulder. Now, she could not use any machine, just lift it up. It's probably pretty heavy. She'd have to use a lot of force. But in this example, she's using a lever, a simple machine, to help her lift that boulder. Okay? So when she uses this lever, how much force is she going to have to apply compared to the amount of force if she were just to lift it on its own? she can use less force to lift it. Okay, that's how this simple machine is helping her. So it's multiplying her force to help her lift this boulder. So if we wanted to figure out how much it's helping her, okay, we can calculate its actual mechanical advantage, the actual mechanical advantage of this lever. The way we do that, the formula, it's the resistance force divided by the effort force. So the key thing to know is that the resistance is the object you're trying to move. So in this case, it would be the weight of this boulder. The effort force is the force it actually takes that you have to apply to use this simple machine. So the force that she would have to pull down on this lever would be the effort force. So which would be greater in this example? Nicole? Yeah, this boulder, you take a lot of force versus the effort she's putting in. So that's how we calculate the actual mechanical energy. Now, is there any friction involved here? Where is there probably some friction that comes into play in this example? Bianca?
Where the pivot is?
Yeah, where the pivot meets the wood of this arm or whatever this is made out of, there's going to be some friction there. So that's going to take some of her force to overcome. So that's why actual mechanical advantage takes friction into account. Ideal mechanical advantage is a different formula. It's the theoretical advantage that this machine would give. And so what we have is distances. The distance you would apply the force, it's called the effort distance. Resistance distance is the distance the object actually moves. So if you imagine her using this lever, after she uses it, how high is this boulder going to go? Jonathan?
Well, it's going to probably go to
I'm going to stop.
probably down there.
Up here? So she pushes down here. Is this boulder going to end up here?
No.
No.
It's going to be even with where the top of it is now.
Yeah, it's probably going to lift, manage, she lifts, it can only get to maybe this high, right? All right, so that's going to be how far the overall distance this object's moving. How about her? When she uses this machine, what distance does she have to apply her effort for? Nicole? All the way down here. So she has to push a greater distance, even though the object only goes up a smaller distance. Okay, so that's going to give you a positive number.
Maybe I
Over
just
one.
slide that down to it.
It might. Depends on the angles there and the friction. So the key thing to know is that ideal, this type of mechanical advantage always is greater than the actual mechanical advantage. Because again, this doesn't take friction into account at all. Even though there is some friction involved when using this simple machine.
Is this safe?
All right, so now we've defined those, we're going to be using them as we talk about each machine. So they should become clear after doing a couple examples. So when we talk about the simple machines, you know, you could group these in various ways. For our purposes, we're going to say that there's 6 simple machines. Although some are kind of subtypes of others, but that's okay. So we're going to say there's the inclined plane, the wedge, screw, wheel and axle, pulley, and a lever. And each of these simple machines can be used to help us to do work. We'll talk today about an inclined plane. So what's another word for an inclined plane? What might you call it in everyday language? Joe? Yeah, a ramp. Okay. But there's other variations that you may not have thought about before about an inclined plane. So an inclined plane allows you to lift an object but allows you to do that with less force than would be without the simple machine. So let's look at our example here. Say we have two individuals. Let's call this Frank and let's call this Tom, for example. Now, Frank is very strong and is able to lift this mass up onto this box very easily. Doesn't need any sort of simple machine to allow him to do that. He just lifts it up there, no problem, and gets it there. Tom, on the other hand, is not very strong. Tom needs, what do you mean?
I don't know. That's your first name.
Oh, what's that have to do with anything? I'm just making up random names. It doesn't mean anything, Jonathan.
Oh, random?
Just random names. So Tom is struggling to pull this object up here. He needs to use an inclined plane. And so he does. So let's think about how this actually works. So the amount of work that's being done, okay? The force that Frank has to apply is 30 kilograms. And the distance the object's moving would be what? 2 meters. Okay? All right. So let's look at how this inclined plane might help. So let's calculate its mechanical advantage. Now, to do that, the ideal mechanical advantage, the formula, is effort distance divided by the resistance distance. So if we think about that, okay, well, what would the effort distance be in using this simple machine? So again, it's a distance. So we're looking for a unit that has a distance with it. What is it, Nicole? Yeah, it's the distance you have to apply the force where you have to drag this weight 4 meters. But how far is the object actually moving where he wants to get it? No? Yeah, you just needs to get it up on this ledge. It's actually only moving 2 meters in the direction it's trying, which gives it a mechanical advantage of what? 2. Now, what about units? This is a tricky one. Bianca?
2 meters per meter.
No? Well, you could say that, but what is anything divided by itself? 1. The units here cancel out. Meters divided by meters, they cancel out. Mechanical advantage doesn't have a unit. It's just 2. So what this mechanical advantage is telling us, you can think of it in several ways. It's multiplying the force that Tom is applying by a factor of 2. Or you might think for him to move this object, he only has to use half the force that Frank did. Okay? So that's what this is telling us. How much is this machine multiplying our force? It's multiplying the force you can apply 2 times. Jonathan?
Shouldn't Tom or Mr. Curie be using 15 kilograms of force because it's supposed to be half?
Well, that's a good point. And I think in a second you're going to realize
I get it for
why.
sure.
Yes. So actual mechanical advantage, again, is a separate type of mechanical advantage we calculate. But remember, it does take friction into account. and we don't calculate it using the distances here. We calculate it using the actual forces that are being applied. So the formula for actual mechanical energy is the resistance force divided by the effort force. So what do you think the resistance force would be in this example? Remember, resistance force. Grant?
30 kilograms?
Yeah, it's the mass of the object, the weight of the object, technically. And in this case, the object is 30 kilograms. That's the resistance force. What about the effort force? Nicole?
16.
Yeah, it's the force that has to be applied when using this machine. In this case, it's 16 kilograms. And so when we do the math here, what do we get for the actual mechanical advantage of this inclined plane? Grant?
What's the minutes?
Well, we don't use fractions. Yeah, let's round. It's going to be 1.9. And like we just said in the previous slide, actual is always less than ideal. So Jonathan asked earlier, before he realized, said, well, it's not actually helping him. It's not helping him make it use half the force. It takes a little bit more. Because this one, as you're dragging up the ramp, what do you have to take into account? Friction. As you use that object, friction is going to, you have to overcome that force as well as dragging the object up the ramp. If you think about it this way, if I have this inclined plane and I use it, okay, I can calculate its actual mechanical advantage by measuring. I can calculate its ideal by seeing how much force I'm applying. What if I then do this? Have I changed its ideal mechanical advantage? No, the distance is the same. The distance is the same. But have I changed its actual mechanical advantage? Yeah, I'm going to have to use a lot more force to drag it up this carpeted area than the smooth wood, because what's greater? Friction. Jonathan?
Wouldn't the train have to overcome air resistance?
Some, but that's relatively minor compared to the friction there. Now, do we use inclined planes in everyday life? Yeah, there's lots of examples. Steps, stairs are inclined planes. You know, we could have designed this school with a ladder for you to get up to the 7th grade hall, and you got to climb up the ladder every time period. Okay? But how much force would you have to use? A lot. The stairs allow you to get up to the same height, but how much force do you apply? But what's always the trade-off? The distance. It's a much farther distance to go up the stairs and up the stairs than it would be to go straight up a ladder. If you ever go hiking and you're going to go up a mountain, what's the shortest distance to get up the mountain? Just straight up. But do any trails actually do that? No, because the force would be too great. Instead, the trail weaves back and forth across the mountain. That's really an inclined plane, allowing you to use less force to get up that mountain. Any kind of ramp is an inclined plane. Any kind of stairs. If you think about the handicap ramp that allows a person in a wheelchair to get in the front of our school, it doesn't just go straight up the stairs. That would take too much force. It goes back and forth. Oh, I just chose some random names. I didn't realize that they would be.
Are those things like the most familiar to you?
Yeah, I just picked them out. Had to come up